Hello, this is Jack Jackson, and I'm going to start a unit here on calculus for multiple integration. This is the 15th unit in this playlist once I get them all done, and it's my third unit for my Calculus 3 class. So we're going to start with an overview of multiple integration in this video. So before we do that, let's talk about where we've been so far in Calculus 3. Our first unit was extending pre-calculus to new types of functions. So if you think about it, one of the things that we're doing all the way through Calculus 3 is taking the ideas from Calculus 1 and 2 and generalizing them to new situations and extending them. So what we did to start with is start with where you start with calculus, with pre-calculus actually, and talk about the idea of a function and relation. And we're going to examine the meaning of those things in new contexts. We're going to be looking at formulas, tables, graphs, words, and context. So what kinds of new functions did we look at? Well, we looked at the ordered n-tuples of real numbers, like ordered pairs or ordered triples, mapped to a real number. In fact, that's going to be the main thing that we're going to be looking at in this unit, those kinds of functions. We also had real numbers mapped to ordered n-tuples. For example, parametric equations did that to us. Real number mapped to a vector. Vector mapped to real number and vector mapped to vector. So different kinds of functions dealing with vectors. We also talked about how to do arithmetic with vectors, how to add, subtract, multiply vectors. And multiplication, there were several different versions. There was a scalar times a vector, scalar multiple type of multiplication, a dot product where you had a vector times a vector to get a scalar, and a cross product where you had a 3D vector cross a 3D vector to get a 3D vector. We also introduced polar, cylindrical, and spherical coordinates a little bit, and we looked at specifically quadratic relations in 2 and 3 dimensions, quadratic functions in those settings. We talked about conic sections and quadratic surfaces as well. So that was kind of our first unit. Our second unit then was extending the ideas of limits, continuity, and differentiation to new types of functions. So we decided what did limits and continuity mean for these various types of functions. We talked about how do we extend the idea of differentiation, specifically in the context of functions of n-tuples mapped to a real number. So we talked about this idea of partial derivatives with respect to x or y, or if you had z, if you had another variable. And then we talked about this idea of directional derivatives in any direction, and the idea of the gradient, which could be built up out of the partial derivatives, and we could use that to help us find the directional derivatives in any direction. Then we put that in place by optimization problems to find extrema and saddle points, and did that in some real-world examples. And then we talked about constrained optimization, and one technique we used there was the technique of Lagrange multipliers. So this is basically where we are at this point in the course. We've made it this far. So this unit, we're going to be talking about multiple integration. So in Calculus 1, we first talked about pre-calculus, then we talked about limits and continuity and derivatives. The next thing we talk about is integrals. Same thing here. We're going to start, as we've done before, by reviewing some Calculus 1 concepts, this time integration concepts. We're going to then see how we extend those concepts of integration to real-valued functions of multiple variables. This is going to lead us to the idea of what's called a double integral, or integrating functions mapping ordered pairs of real numbers to a single number. Take those kinds of things and see how we can talk about what's meant by a double integral. We'll define that concept and learn how to approximate it. Then we're going to look at the idea of iterated integrals, which are really sort of the idea of partial integrals iterated together. And this will allow us, we'll be able to use the fundamental theorem of calculus in this way. And we'll be talking about concepts and definitions, approximations, using the fundamental theorem of calculus, and our Calculus 1 and 2 integration techniques will then be applied here. After we've done double integrals, we'll move on to triple integrals. We'll talk about changing the order of integration and integrating with different coordinate systems, and we'll do a few applications of that. So that's going to be what we're going to be looking at here. So the general idea throughout Calculus 3 is how do we take the concepts and skills of Calculus 1 and modify or extend them to work in the context of new types of functions? What stays the same and what must be modified? In this unit, we're specifically going to say, how do we take the Calculus 1 concept of integration of a real valued function of a single real variable, Cal 1 way of doing it, and how do we translate that to the context of integrated a function of two or more variables? What stays the same and what must change? So here's kind of a side-by-side look. On the left we have Cal 1, on the right we have Cal 3. Definite integrals of a single variable on the left, double integrals on the right. So just a quick overview, the approximating integrals with the Riemann sum on the left. We break the interval into subintervals for the base, evaluate the function at some value in that interval for assigned height, multiply those two things to get an area of a rectangle, or at least a signed area, and sum these areas to get what we call a Riemann sum. We're going to do the same kind of thing in Cal 3. We're going to approximate an integral with a Riemann sum. We're going to break the region, which is a rectangle, let's say, into subrectangles for bases, evaluate the function at a value in the rectangle for assigned height, multiply those together to get a volume of a rectangular prism, and sum those volumes to get a Riemann sum. We can approximate that by the integral from a graph or a table. We did that in Cal 1. We're going to do that in Cal 3 as well. Now, once you have this Riemann sum, then we can take the limit of it to get an integral. That's how we did it in Cal 1. That's how we're going to do it in Cal 3. That integral represents the net area under a curve, well, a signed net area. Area above the x-axis is positive and below is negative for the definite integral of back in Cal 1 and Cal 2 of a single variable. But when you're doing Cal 3, we're looking at that becomes a volume. It's a net volume under a surface, a signed net volume under a surface. In Cal 1, the fundamental theorem of calculus connects the definite integral to antiderivatives, and so we were able to reverse our derivative shortcut rules to obtain certain antiderivative techniques, and we learned some of those in Cal 1, and we did some more advanced techniques in Cal 2, and that allowed us to use the fundamental theorem to evaluate integrals directly, definite integrals, via, I guess indirectly actually, by going by way of the fundamental theorem. We're going to do a similar thing over here in Cal 3. We're going to look at the fundamental theorem of calculus, and it's going to connect iterated integrals to antiderivatives, actually partial antiderivatives, sort of the reverse of partial derivatives. And then we're going to see a double integral is equivalent to an iterated integral. And then we'll apply our integration techniques and the fundamental theorem that we learned back in Calculus 1 and 2 to these integrated integrals, and that's going to allow us to evaluate them exactly, which is in turn going to be the same as evaluating the double integral. And in the next few videos, we'll go over these things in more detail. If you don't follow everything that we did here at this point, that's fine. This is just a quick overview, and we'll look at the details later in the next video.